All right, so this is 5.2 logarithms, and we're going to be making lots of connections between exponentials and logs because, of course, logarithms are inverses of exponentials. So let me just start off. Suppose f of x equals a to the x for some a in one of our two cases, either this case or this case. Okay, so a has to be either in the case of exponential decay or in the case of exponential growth. And here we have an exponential. Okay, nothing new yet. Now, I just want to point out quickly here, this is often written as a greater than 0 and a not 1. You can see that these are equivalent. Saying that a is greater than 0 and not 1 is the same as saying a is between 0 and 1 or bigger than 1. Okay, I actually prefer the first one because it clearly separates it into our two cases of decay and growth. Okay, so I find it's a little bit more descriptive. This one down here tends to be a little bit more common, and you want to guess why? You got it, less writing. That's it. So anyway, I just want you to notice that there's both of those. Now, suppose we have this, then by definition, okay, the inverse function f inverse of x is log base a of x. Okay, so let's be really clear on this. We've got some set of inputs and some set of outputs, and we have a function f, and f maps different inputs to different outputs. Sometimes they could be the same output, but it's never one input to two outputs because then that's not a function. This is coming back to unit 1. But regardless, anyways, so we map inputs to outputs. And if we want to start with a given output and figure out, hey, what was the input that got us there? That's what the inverse does. And what we're saying is if our function that takes inputs to outputs is this function right here, the exponential, then the function that takes outputs, this x here is actually the output from the exponential function. The function that takes outputs and tells you what the input was in the first place, that's called log base a. That's the function. Okay? Now, it's important to note we haven't actually said what log is. It's not like I have a formula for log. All I've said so far is log is the thing, the function that gets us from the outputs of an exponential back to the inputs. It is the inverse. But how to calculate it, that we still need to do some more work. Okay? Really important conceptual piece here. This, I don't think you need to memorize it per se. I don't really know what code to use. I think I should develop these codes actually. This is sort of like, I don't know, critical understanding or something. And I think that for many of us, it's going to take some time to fully absorb what's going on here. Okay, so I've done that. Yeah, and so I made a little note to myself. I said that this is actually what makes logs kind of tricky for a lot of people, is the recognition that we don't actually have a formula for a log. A log is just a name that we give to the inverse of an exponential. But there's no formula here. Okay, so now I've got a quick question coming back to Unit 1. If f and F inverse are inverses. Obviously, by notation, they're supposed to be. So if these are inverses, or assuming they're inverses, or given that they're inverses, probably given is better, because they are actually inverses. So given F and F inverse are inverses, how do their graphs relate? Okay, that's my question. This brings us back to Unit 1. At this point, I might actually ask you to sketch a graph, F, and sketch its inverse. In fact, why don't you do that? Pause and sketch f of x equals x squared, and then the inverse of that. F of inverse of x is, well, we don't really know. I mean, I know, but just based on the graph of this, what would the graph of this look like? Pause the video and try it out. Okay, so you should have here a parabola. Well, that's pretty wonky there. That's a little better. Okay, a parabola. Here's the line y equals x. And why am I putting the line y equals x? Well, because in fact, to get the inverse, you switch the x and y and solve for y. You switch the places. What that has the effect of doing is switching all the x and y coordinates, which visually gives you a graph that's flipped over the line y equals x. We could go into more details as to why this is, maybe some other time. We did talk about it in Unit 1. But in a nutshell, what we get here is a parabola on its side. That's the inverse function. Okay? Now, why am I bringing this up? Well, it's just an example of how the graphs relate. What I want you to take away from this is the graphs relate by being mirror images when reflected over the line y equals x. So I'll put that. The graph of, let's say, F inverse is the reflection of F in the line y equals x. And the graph of F is the reflection of F inverse in the line y equals x. Okay, so this is important. Why is this important? Because this is going to help us start to graph logs. Because logs are inverses of exponentials, and we know how to graph exponentials. That was the last unit, right? So we know how to graph these exponentials, and now, because the log is the reflection over the line y equals x, we're going to be able to graph logs. All right, so I want to go through 4 cases here, and we're just going to go really methodically. So the first one is f of x equals a to the x for a greater than 1. So by this point, you've hopefully memorized that it is exponential growth, key point 0, 1, comes up like this, goes down like that. Okay, I would mark myself wrong, by the way, on a test. You see how this, you see how this slope comes back up? That's too sloppy. Okay, unless you have a good reason, you should be able to draw right down closer and closer. Okay, so be careful. So that's the exponential. What are some key facts here? Well, we have the key point 0, 1. We have the domain. I'm just going to do it the quick way, all reals. We have the range, quick way, y is bigger than 0. We have an asymptote. y equals 0. And here's another fact that I didn't really talk about before. The slope of the curve is always positive. It gets steeper and steeper as we go, right? If I take orange, at this point, the slope is a very shallow positive. At this point, it's a much steeper positive. But regardless, anywhere you go, the slope is positive. That's actually one of the reasons why this is so bad, because it shows a negative slope, which is false. Okay, so the slope is always positive all the way through. Just trying to get rid of these orange dots. There we are. And there's a way to write this. The slope of y, of the curve given by y, the slope of it is called y prime. Y with a little slash. And I'm going to say that slope is always positive. It's bigger than 0 for all x's. Here's a special symbol for all x's. For all. Okay, we're going to come back to this several times, actually. This idea that the slope is always positive, this is our next connection to calculus. Thinking about slopes. We talked a bit about limits. Now I'm talking about the slope. Okay, we're not doing calculus, but we're thinking about calculus. Okay, now I want to do the graph of f of x equals a to the x for the other case we have. This is exponential decay. We've memorized this one, or we're in the process of memorizing it. See, that's really bad there. I do apologize that I can't draw these very well. There we are. That's better. And up like this. Okay, so there's exponential decay. We've got the same key point, 0, 1. That's because anything to the exponent of 0 equals 1, unless a is 0, but that's excluded. The domain, all reals. The range, same thing, y bigger than 0. You know, compare back and forth between these two cases. So far, everything's the same. We have an asymptote, y equals 0. Here's where we have a difference. This time, the slope is negative for all x's. Right? This here is a way of writing the slope is always, well, actually, let's be a little more literal in my translation. The slope is negative for all values of x. Okay, and you can see that. You can take any point here, you draw the point, you draw a tangent line, you can see the slope there is negative. Even down here, it's a shallower slope, but it's still negative. Okay, so the slope is always negative in exponential decay, which makes perfect sense. That's why it's decaying. It's getting smaller, negative slope. Okay, now I'm going to take each of these and use it to get the graph of the log function. Remember, the log is the inverse. So in this case, I'm going to look at f inverse of x is log base a of x. That's how we say it. And I'm going to graph this. And what I'm doing in my head is I'm taking this curve here and I'm reflecting it across the line y equals x. Okay, so as I do that, this is what I get. First of all, this point, 0, 1, switch the x and the y, 1, 0. This part here will look like this. This part here flip it over this line, will look like this. You see? See how my exponential has been flipped over the line to get me this log? Okay, so this is the graph of a log with a greater than 1. Okay, right here. By the way, this is the, well, I shouldn't say it. In applications, this is probably the more common case, not this one. But they're both good and useful. Okay, so this is for a greater than 1. That's it. That's what it looks like. And now let's go through each of these things here and look at what's corresponding. Key point, well, in inverse, you switch the x and the y. So the key point here is 1, 0. Domain. Okay. The domain, you can see we start at 0 and go up. That's the same as the range of the other one. Start at 0 and go up. Right? We're switching the x's and y's. So when you put an x here, you get x greater than 0, and that is in fact the domain. My domain here is x bigger than 0. I'm switching my x's and y's, so this x would become a y. It should be y is all reals. That's what we would expect. Is it? Yeah, it is. Right? We're coming up and getting all the reals here, and we get certainly all the reals down there. The range is all reals. And you can get that literally by switching the places of x and y everywhere. Asymptote. Well, switch x with y. Your asymptote is x equals 0. And you can see it on the graph. X equals 0. There's our asymptote. So my asymptote is x equals 0. What about this slope business? Now, here you can't just switch x's and y's because, well, this is a y prime. This is a derivative. It's not a y. It's a y prime. It's something else. So here now, we have to kind of look at it. Here, what's the slope? Positive. 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 The slope is positive everywhere. Okay, so we would say, whoops, let's get this cleaned up. There we are. We would say that y prime, the slope, is bigger than 0 for all x's. Okay, this says the slope is positive for all values of x. That is, all values of x that are in the domain. We know that the domain is restricted. I don't have to repeat that down here. Okay, for all x's that are in the domain, the slope is positive. And that's it. That's the key information. There you go. This is the graph of, well, you can call it f inverse of x, or if you prefer, you could call it y equals log base a of x. Same thing. There's the graph. Okay, now we're going to do one more. We're going to do the case where a is between 0 and 1. By the way, just because it popped into my head, you can also write this in other notations. Remember that notation? That's the same thing. Or, remember this notation? This is my least favorite. And I think most people in North America, it's their least favorite. Even in Europe, from what I'm aware. I better not speak on Europe. I'm not 100% sure. But anyway, that means the same thing. Right? So there's different ways to say it. That's in Unit 1. But I'm just writing it this way, and that's fine. Okay, so again, I have the line y equals x. I am reflecting this exponential decay graph about this line y equals x. This point where they intersect won't move. Everything else will move. This jump will become a jump like that. And this here will become this here. And this point, 0, 1, x's and y's switch will become 1, 0. Okay, so I get a graph like that. Okay, so I'm going to do that on a separate graph so that I don't muck up the first one. Doop, doop, doop. Woo, okay, there we go. So I'm going to do f inverse of x. I'm just calling it f inverse to emphasize that it's the inverse of the exponential function. We could also just call it y and have this to be the y-axis, right? So I've got this point here. It goes up like this to this asymptote of x equals 0, and it swings out this way. Okay, and that's it. That's the graph. Key point, 1, 0. You switch the x's and the y's up here. Switch the x's and the y's, you get 1, 0. Switch the x's and the y's, we're going to get a range of y's all reals, a domain of x is greater than 0. And indeed, you can look at the graph and you can see that that's true. The domain is x is greater than 0. The range is all real numbers. What else do we have? Asymptote. Switch the x and the y. That's going to be x equals 0. And sure enough, you look at it, there's the asymptote. X equals 0. And what else have we got? Well, then we talked about the slope. For that, I want to actually look at the graph. Let's take some points. So way up here, we have got a negative slope, a very steep one. Here we have a negative slope. Less steep, but still pretty steep. Here we have a negative slope. Here we have a negative slope. Here we have a negative slope. In fact, along the whole curve, we have a negative slope. By the way, we'll be able to prove that algebraically later on when we have calculus. We can demonstrate that. But for now, we're just going to look visually, and we can see that we've got a negative slope the whole way along. So I'm going to write that as y prime, the slope, is negative for all x that are in our domain. Now here's where I'd ask you guys, do you want it in words? And I kind of look up, and some of you might nod, and I'm not really sure. So I'll put it in words. The slope is negative for all values of x. Again, a quick reminder, this symbol here means for all. One for all and all for one. Okay. I'd love to ask you questions, but of course, it's really hard just talking to a computer and imagining you all listening and, well, I don't know, smiling, frowning, scowling, doodling. Hope you're paying attention. Okay. So let me do this here now. Whoops. Consider the transformation from y equals f of x to y equals a f of q onto x minus h plus k. How could we introduce these parameters into the equation y equals log base a of x? Okay, so the question is, how could we introduce, I'm going to call it an A star again, Q, H, and K to y equals log base A of x? That's my question. And this is actually where I would pause and I would ask you guys to puzzle it out. And I'd probably say, give me a thumbs up when you and somebody near you both have the same answer. It would be a good question for that. So why don't you pause the video, see if you can puzzle it out, and then unpause and see if you got the right thing. Okay, so you should have y equals, now a star is going to come first. We're always multiplying the function by a star. My function is a log, so this a star is coming in front of my log. Okay, times the function itself. The function is log base a of something. The argument is being transformed from x to, what's the argument here? Here, the argument of the function is q onto x minus h. So the argument of my function is going to have to be q onto x minus h. Just like that. Argument, argument. And then the plus k, you can see, if I emphasize it here, here's my f of, and my plus k is after the function itself. So my plus k is going to be after the function itself, like so. Okay? So I'm going to erase some of this so it's cleaner again. Got a few little dots in there. And I'm going to erase a little bit here so it's cleaner again. Okay? This is what you hopefully got. Or maybe you got something close to it. This, I would memorize. This too, by the way, actually. This, I would, whoa, well, here we go. This, I would make sure, if I were in your shoes, that I knew that. Ideally, this one here you could derive. The first one you should really memorize. The second one here, ideally, you could just be able to generate it. That would be the best. Okay. By the way, coming back up here, you should be able to derive these pretty easily. And being able to derive these, you should then therefore be able to derive these. Okay? I wouldn't try to memorize them from scratch. That's an awful lot to memorize without understanding. You should practice being able to generate them. I would call this sort of a process. Starting with this exponential equation and exponential decay equation, generate that and that as well. Okay, so here we are. We've got y equals a star log base a onto of q onto x minus h plus k. And, well, that's it. Okay. So now why do I want to do this? Well, obviously, so that I can apply transformations to logs. So let's take an example. Let's suppose we are asked to graph 1.5 log base 2 of 1 onto x minus 3 minus 2. What do we do? Well, first we plot log. So I'm going to bring up some graph paper here. And I'm going to graph, first of all, I'm just going to graph y equals log base 2 of x. 2, by the way, is bigger than 1, so we're looking at the a greater than 1 case. In that case, we've got our grid here. We have a point right there at 1, 0. That's because in an exponential we have 0, 1. And this comes up like this and down like that. For now, that's enough. Okay, however, I happen to know some other points that will be on this, so I might as well put them in just to make the graph a little bit more accurate. I happen to know that we're going to have 2, 1. I happen to know that we're going to have 4, 2. I happen to know that we're going to have, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, sorry, 8. Get back. 3. And I happen to know that we're going to have 1/2 comma -1 and 1/4 comma -2, whoops, and so on. Goodness gracious. Okay, so I'll get a better shape. We will discuss how I got those points later. Okay, I've got the shape here. Now, I'm graphing this guy here. So I need to first stretch all the y-coordinates by a factor of 1.5. This y-coordinate won't move because the y-coordinate here is 0. 0 times 1.5 is still 0. This one, however, will move up here. 1 times 1.5 is 1.5. This one, 2 times 1.5 will become 3. 3 times 1.5 will become, what is that, 4.5. Okay, so this will stretch like that. -1 will become -1.5. -2 will become -3. So it will continue to stretch down there as well. Okay, so now this one here is y equals 1.5 log base 2 of x. The original one was y equals log base 2 of x. Now I've got a shift to the right by 3. That's my h right there. And I also have a shift down by 2. That's my k. So every point on the light blue line, I'm going to make those shifts. So here I go 1, 2, 3, 1, 2. 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 Okay. Here 1, 2, 3, 1, 2. Whoops. No, that's the wrong point. That was from the dark blue. Light blue. 1, 2, 3, 1, 2. Okay. And the asymptote shifts 1, 2, 3. So I have a new asymptote line right here, x equals 3. I don't need to shift it down because it goes infinitely. So now I can connect these dots, create my graph. Y equals 1.5 log base 2 of x minus, what was it, 3 minus 2. Okay? So this is how we apply transformations to logs to graph them. It's also a bit of a review of transformations in general. And there we are. It's the red one. Love to ask for questions. Wish I could. Okay, so now this altogether gives us enough for exercise 9F. Okay, 9F. You know what I might do? I'm going to do a little bit more here, but I'm going to put in another video just so that I can upload them sequentially. Okay, so I'm going to end off this video and then I'm going to do one more.